الو دکتر بس به زحمت
بله كرمك.
دكتور بس أزل خسته ديخشكم إنه كعملي كان جبر غيابات أما خطي باقي درست أسنى ما المحاصرة ده
لا درست السلامتية إن شاء الله، لا مشكلة يعني.
أرد صاحبي دكتور خدش تلاصي بيتم
سر شوا بخيراتي.
صاحبي قالك ممنون.
سر شوا. يا الله. يا الله. Okay, now we are going to start with a new topic, which is the separate spectrum techniques. This is a very important topic, and in this lecture I'm going to today I'm going to cover the basic separate spectrum systems, which are the direct sequence and the frequency hopping separate spectrum systems. We'll talk about the transmitter and receiver of each system individually. First of all, let us talk about the separate spectrum generally. Really, a new technology at the beginning, it will be used where in the military field. Then it will be moved to the commercial field. So look at the history of the separate spectrum. There was intensive use of communications warfare during the World War II. This technique outlined the ability to intercept and interfere with the hostile communication. Okay, hostile means al-muadi. Firstly, development in communication theory initiated encryption schemes by Shannon law formula, as you know, in 1949. As I think you are familiar with the Shannon law formula, which is what? C equals to B log 1 plus S n R. Of course, log base 2, and C represents the bit rate of the channel, and B will be the bandwidth of the channel. So the bit rate relates to the bandwidth and the signal to noise ratio. Secondly, work was initiated to harness the development of the new technology. This technology is called the separate spectrum techniques, which exchange the bandwidth expansion for communication security and targets ranging for what? For military applications. Now, we have benefits and say some advantages of the separate spectrum system. First one will be avoiding interception. Okay, avoiding interception in military communication. Interception of hostile communication is commonly used for what? For various operations, such as what? Identification. I mean, to identify the kind of the target. Okay, whether it's a airplane, something else. Okay, missile, and so on. Jamming, jamming, it means jamming will lead to losing the control on, for example, a hostile missile or an airplane missile. Surveillance or reconnaissance, this is called in, will be أنظمة الاستطلاع, reconnaissance system. Now, the successful interceptor usually measures the transmitted power in the allocated frequency band, thus spreading the transmitted power over wider band undoubtedly lowers the power spectral density, and thus hides transmitted signal information within the background noise. So in this way, when we have an ordinary receiver, not a separate spectrum receiver, that receiver will sense the information signal or the trusted signal as as noise. So you can do your communication in secure way. The intended receiver recovers the information with the help of with a system processing gain. At the end of the lecture, we will be able to understand what I mean by the processing gain, which is a very important parameter in the separate spectrum system. Second benefit of the separate spectrum system is the privacy of transmission. Okay, the transmitted information over the separate spectrum system cannot be recovered without the knowledge of the separating code sequence. Now, after say 10 minutes or more, I'm going to explain what do you mean by separating code. Of course, to transmit a signal, first of all, the message signal M of T or the binary bits are multiplied by what? By chip code. Okay, chip code. This chip code will lead to separating the energy of the bits over wider bandwidth, or in other words, we say the bit rate will be increased. So at the transmitting end, if you don't have the separating code, at that time it will be impossible for what? To recover the original signal. So in this way, we can provide good privacy for the transmission and for our information. And it's very difficult, for example, to anyone to listen or steal the important information of that line. 3, resistance to fading. Of course, to understand what do you mean by fading, we have to go to the whiteboard to explain what do you mean by fading. I don't know, are you familiar with this word or not? Have you studied fading or not? No response. أري تورقبت ودي fading موضوع fading.
إذا منى attenuation
in communication building communication system fading okay, now let us explain what do you mean by fading. Now in any communication system we have a transmitter, okay, and on the other end we have what we have a receiver RX and TX. How we are going to transfer the signal between these two endpoints? Of course, through a channel. In multipath communication system, we have the following. We have line of sight signal. Okay. We have what? We have another signal, which is what? Reflected signal. And we may have ground reflected signal. Again, we have another kind of signal due to, for example, high buildings. We have another kind of signal called scattered signal. Okay, so this one will be what? Will be a reflected signal. Reflected signal. This one again, ground reflected signal. And this one will be scattered signal. And the first one is called what? Line of sight communication. Okay, so as you can see, here we have what? Here we have multi copies of the transmitted signal where at the receiving end. These multi copies are arrived with what? With different delays. Well, so we may imagine that at the receiving end we have the following. For example, x of t, we may have x of t minus tau, x of t minus, for example, 0.5 tau, x of t minus 2 tau. As you can see, the same signal, I mean the x of t, is sent and it's received by the separate spectrum receiver, but with what? With different time delays. Of course, if you are going to directly process such a signal, we will have weak signals. Okay, different phases. So the signal will be the magnitude, I mean, of the received signal will be reduced or become weaker, or in other words, we say fading signal. Now, let's go back to the the resistance of separate spectrum signals to multipath fading is brought about by the fact that multipath components are assumed to be what? To be independent. Okay, this means that if fading attenuates one component, the other components may not be affected, so that unfaded components can be what? Can be used to recover the information. Again, we have another application for the direct sequence or the separate spectrum system. Sorry, it is accurate low power position finding. Using the separate spectrum, we can determine the location of the target or even the mobile users accurately based on the what? Based on the signal to travel and back to the original source, and range in meter can be determined by 3 multiplied by 10 to power 8 transit time over 2. Now, of course, we may simplify this equation. Look, In practice, the transit time is determined by monitoring the correlation between the transmitted and received code sequence. The transit time can be computed by multiplying the code duration by the number of code bits needed to align into sequences. Look, TC, the time of the chip, and N number of chips. And you said that transit time over 2, so it will be 3 multiplied by 10 to the power 8 over 2, it will be 1.5 NTS multiplied by 10 to the power 8 meters. The range resolution requires the chip duration TC to be small, I mean using high frequency, in order to get accurate results. Another important point is what is the improved multiple access schemes. As I think you are familiar with the FDMA, TDMA systems. In FDMA and TDMA system, for example, in FDMA, say, in FDMA, we are going, for example, to assign a channel for a specific user. When the call is finished or ended, that channel will be rebacked and to be ready to be used by another user. So we don't have dedicated channels for every user. Now, in separate spectrum system, we are going to use the code division multiple access technique to enhance the multiple access techniques. Digital transmission schemes which provide satisfactory performance and adequate bitrate can be arranged into 2 categories. In applications like satellite communication, these schemes provide efficient usage of the limited power available. We said that we are going to separate the signal over wider bandwidth, but on the other hand, what will happen? On the other hand, the magnitude of the signal will be decreased. Okay, so the required power will be again is decreased. In applications such as mobile wireless, where the schemes achieve efficient usage of the limited bandwidth available for the service in demand. Of course, again, we may use the CDMA for efficiently utilize the available bandwidth for the communication. Bandwidth expansion in separate spectrum is acquired through a coding process that is independent of the message being sent or the modulation being used. Now, to understand the operation of the separate spectrum, we have 2 examples. Rapidly, I'm going to talk about the solution of these examples, and then we'll move to the transmitter and receiver of the direct sequence separate spectrum system. Now let's go to the example number 1. Example 1. Binary data is transmitted through an additive wide Gaussian noise channel with SNR equal to 3.5 dB. Okay, so we have SNR is equal to 3.5 dB and bandwidth B. The bandwidth is B. Channel coding is used to ensure reliable communication. Okay, then what's the maximum bit rate that can be transmitted? So we have to determine RV in this example, or C. Well, and in the branch B, if the bit rate is increased to 3B, how much must the channel SNR be increased to ensure reliable transmission? Now, here we are going to talk about the separate spectrum technology principles. In these 2 examples, these are very important 2 examples, example 1 and 2. These 2 examples will illustrate the benefit of the separate spectrum and its operation. Basically, you have to keep in your mind the following. Now, in ordinary communication systems, say this will be the y-axis, and this is the x-axis, I mean f in hertz, and this will be the magnitude of edge of f. Well, this is what in the ordinary communication system we said. And what will happen? We have a center frequency, say Fc, I mean the location of the carrier frequency. And here we have what? Here we have a band pass filter. Okay. Here it's band pass signal. This is the ordinary communication system. Now we have another technique, which is what? We are going to transmit the same information, but with the following modification. In this time, this will be happen. Look. Now the signal level is reduced while the bandwidth is what? Is increased. For what? To keep the same amount of energy. Okay, so we have the same amount of energy in time and in frequency. And if you are going to follow the method of this one, for example, increasing the bandwidth, really it will enhances the communication system. Well, these techniques is done based on what? Based on the Shannon law formula. Look there at Shannon law formula. C equals to B log 1 plus SNR and base 2. Okay, we have base 2, 1 plus SNR. Now, as you can see, reducing the SNR, you have to increase what? The B. Or when you are going to reduce the B, you have to what? You have to increase the SNR in order to what? In order to keep the same amount of bit rate or the channel capacity. This is the idea of what? This is the idea of a separate spectrum system. So if you are going to adopt or develop a system based on the separate spectrum principles, at that time we have to what? We have to allocate a wider bandwidth, or greater bandwidth must be allocated for what? For the separate spectrum technology. Now, going back to our example, in our example, it's talking about what's the maximum bit rate that can be transmitted based on, of course, the conditions and assumptions given in the example. Now, of course, as I have told you, we are going to follow this formula. I mean, C equal to B log base 2, 1 plus SNR. And SNR is given by 3.5. SNR equals to 3.5 dB. You have to convert this dB into ratio in order to be able to apply this value in the formula. So SNR in ratio will be 10 to power 0.35, and it will be 2.24. Okay, now we can substitute in the previous equation. So C equals to B log 1 plus 2.24, sorry, 2.24 base 2. Don't forget, it's base 2. So if you are going to simplify this one, of course, you are going to apply this formula. B equals to ln 1 plus 2.24 divided by ln 2, and the result will be 1.7 B. This is what? This is the bit rate of the channel. Now, in the branch B of the same example, it talks about if the bit rate is increased to 3B. Look, now bit rates, I mean C. C becomes what? Becomes a 3B. Okay. How much must the channel SNR be increased in order to what? To ensure reliable transmission. In this time, we have to what? We have to increase SNR to compensate the effect of what? Increasing the bit rate to a 3-bit. We said that either keeping the bandwidth constant or either keeping the bit rate constant. Of course, usually we are going to keep the bandwidth constant and increasing the signal to noise ratio in order to compensate the enhancement in the channel capacity or the bit rate of the system. Well, based on the same assumption, now again we are going to follow the same formula: C equal to B log 1 plus SNR base 2. Now we have the transmission rate or the bit rate becomes 3B equals to B log 1 plus SNR base 2. Of course, SNR is unknown, so the B, this one and this one will be cancelled from the both sides, and here we are talking about len 2, len base 2. So to get rid of from the logs 2, we are going to take what? 2 to power. So right side will be 2 to power 3, I mean 8. Okay, 8 equals to 1 plus signal to noise ratio. And you will be able to determine the signal to noise ratio very easy and simple. Now, the SNR now, it will be 2 to power 3. Look, 2 to power 3 equals to 1 plus SNR. And this will be 8 equals to 1 plus SNR, and SNR equals to 7. Okay, this will be the signal to noise ratio in the system. Of course, you can convert it into the dB by what? By taking SNR now in dB will be B log base to 1 plus 7. Okay, that's it. This is the example, the first example, solution of first example. Now, let's go to what? To example number 2. In example number 2, again, we need the same formula. I mean, the Shannon-Rowe formula will be used. Binary data is transmitted at a rate of RB bits per second over a channel occupying a bandwidth B, and the channel SNR equal to 3. Okay, so again, here we have the bandwidth is given by B, and bit rate is given by RB bits over second. Yes. Now, and the channel SNR is equal to 3 dB if the bit rate is increased to 2.65 RB and the bandwidth is increased to 1.75. Determine what would be the channel SNR for the new system. This is the first thing. And the second branch, we are talking about what channel bandwidth is required to keep the same channel signal to noise ratio. Now let's go to the branch 1. In the branch 1, then we are going to move to the other branches. First of all, here we have in the example number 2. In example number 2, example 2, we have the following. SNR equals to 3 dB. So SNR in ratio will be 10 to power 0.3, and it will be about 2. Well, now, based on the information given, we can construct 2 equations. Look, please, to understand what's going on. If the bit rate is increased to 2.65 RB, okay? Now, at the beginning, we have RB. So I'm going to utilize the same formula, which is C equal to B log 1 plus SNR. Now, at the beginning, we have RB equals to what? B log 1 plus SNR, okay? And the SNRN ratio is 2, okay? So RB equals to B log of 3, okay? No more, no less. Now, you can say that this equation will be equation number 1. Now, for equation number 2, what channel bandwidth is required to keep the same channel signal to noise ratio? Okay, so in the second branch, we need what? We have to determine the channel bandwidth B is required to keep the same channel signal to noise ratio. Now, look at the second line of the problem. It talks about if the data bit rate is increased to 2.65 RB. So we can reconstruct another equation. Now, second equation will be more simpler than the first equation. Why? RB is already given, so it is 2.65, sorry, 2.65 RB equals 2. Now, in this time, look, the bandwidth is increased to 1.75 B. So here we have 1.75 B log 1 plus SNR. We said that SNR in ratio is equal to 2. Now, what we are going to do for the next step, of course, for the next step, we are going to do the following. Page 2, of course, don't forget. And now we can divide equation 1 over equation 2. If we are going to divide equation 1 over equation 2, then we have the following formula. 1 over 2.65 equals to B over B dash. Thus B dash equals to 2.65 convert to with 1.75 B. Okay, now we have B over B dash. So B dash will be 2.65 B capital. This is again about the example number 2. Really, in these two examples, we have discussed different ideas about the Shannon law formula, which is utilizing the spreading of energy over wider bandwidth. Now let's talk about the most commonly used separate spectrum systems. First one is called direct sequence separate spectrum, and the second method will be the frequency hopping separate spectrum system. Now let's go to the direct sequence separate spectrum transmitter. Of course, to transmit such a signal, first of all, the message signal M of t will be multiplied by chip code. Of course, to multiply, I mean multiplication here in this topic or this subject will be implemented by exclusive NOR gate. Okay, please don't forget to use exclusive NOR gate. Previously, when we talk about the exclusive OR, we said that when they are the same, the answer will be 0, and when they are different, the answer will be what? 1. I mean, talking about what? About the output of the exclusive OR gate. Now we have exclusive NOR gate. So when they are the same, it is 1. When they are different, will be what? Will be 0. So first of all, the spreading of data is performed by what? By multiplying the high rate code sequence to acquire the energy spreading. The baseband signal Sn of t is filtered to confine energy within the bandwidth defined by the code rate. Carrier modulation is commonly used in separate spectrum is what is phase shift keying, and in sometimes you are using the frequency phase shift keying. Okay, so frequency shift keying, and we have different kinds of the frequency shift keying. For example, 2FSK, it means binary FSK. 4FSK, quadrature. Okay, and we may have, for example, 8FSK, 16 FSK, and so on. Okay, this is depend upon what? Upon the symbol and bits. So, for example, every symbol is represented by 3 bits. At that time, we have, for example, 8 phases and so on, or 8 frequencies. If we are talking about the frequency shift keying. Well, point number 4. The baseband signal is convoluted with the impulse response of a spectrum shaping filter to yield y of t. Let's go to the diagram. As you can see, here we have the message signal of information signal m of t, and here we have the code c of t after multiplication. This multiplication will be implemented by using exclusive NOR gate to get what? Get Sn of t, and then we have a filter edge of t, and finally we are going to multiply by the final carrier, and then the signal will be transmitted over the channel. Now, to receive the direct sequence separate spectrum signal, we need a receiver. Of course, the most important stage in the receiver will be what? Will be the stage of coherent carrier. Of course, what do you mean by the word coherent? Okay, what do you mean by the word coherent? Coherent means we are going to generate locally under the receiver. In the receiver, we are going to generate a cosine signal which has the same frequency and the same what? The same phase as of the incoming or interested station or signal. Then it will be multiplied by C of t to recover original signal, matched filtering, and then we have the 3-shoulder circuit. Now, here we have an example. This example is a very interesting example. I'm going to solve this example to show you how we are going to perform the spreading operation. Another example. A binary data stream of 4 digits, which is 1011, is spread using a chip code C of t. Now, C of t is given here, and it is 0, 1, 1, 0, 1, 0, 0, 1, 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 chips. Chip code is 8 chips, so it's 8 bits. Now, the separate data phase modulates a carrier. Now, please, do you remember what do you mean by the phase modulation or binary phase modulation? In the binary phase modulation, we have only what? 2 phases. First one will be the 0 angle, and the second one will be what? Will be 180 degree or pi. So, how we are going to provide such a thing? Of course, after performing the mapping operation. Mapping operation will help us for what? To convert 0 into 1 and 1 into -1. So again, I'm going to perform the multiplication operation by using exclusive NOR gate. Look, please. In the first stage, we have m of t multiplied by what? By c of t. We said that we have an exclusive NOR gate. So take bit by bit. Now, starting from this one, now, 1 exclusive NOR 0, it will be what? 1 exclusive NOR 0, it will be 0. They are different, okay? 1 exclusive NOR 1, 1, 1, 0, 1, 0, 0, 1, okay? This is the what? This is the first bit. I'm sorry, I have to move to the whiteboard screen. Please look at the screen. I'm going to repeat it. Now, example, we have the binary bit M of t 1 0 1 1, and C of t is 0 1 1 0 1 0 0 1. Now, I'm going to perform the exclusive NOR gate with each bit in the chip code. One exclusive NOR 0, it will be 0. Why? They are different. Here, one exclusive NOR 1 will be 1. One exclusive NOR 1, 1. One exclusive NOR 0, it will be 0. One exclusive NOR 1 will be 1. And with these two zeros will be 0, and final one will be again 1. This is the operation of what? This is the operation of exclusive NOR gate. Well, for the second bit, we have 0. Okay, as you can see, here we have 0. So 0 again, exclusive NOR with 0, it will be 1, of course. Okay. Now 0 with 1 will be 0. They are different. 0, 1, 0, 1, 1, 0. This is what will be the second bit. The third bit will be 1, 0, 1, 1, 0, 1, 0, 0, 1, and the fourth bit again will be 0, 1, 1, 0, 1, 0, 0, 1. As you can see, the 4 bits becomes what? Becomes 32 bits. I mean, every bit is represented by what? By 8-bit. Of course, this is in what? In the simpler systems. Actually, we have, for example, 16-bit, 32-bit, and 128-bit, and so on. Now, this is about what? About the first stage, I mean, separating the information signal. Now, this signal is called what? This one will be MS of T. It is the separated message. 4-bit becomes what? Becomes 32 bits in this example. Now, of course, to simplify this thing, we have to prepare the following diagram. Here we have a transmitter, channel, and what? And the receiver. Up to now, we are working where? Inside the transmitting end. Okay. Up to now, we have prepared the MS of T. Next stage is what? To multiply MS of T by cosine omega CT. Okay. Now, so at this point, we have MS of T multiplied by what? Cosine omega CT. Now, after the signal will passes through the channel, the signal will be exposed to interference. The interference component in the channel will be what? Will be cosine omega CT plus what? Plus 30 degree. So we have the same frequency, and then we say what? We say interference. If we are talking about another frequency at that time, there is no interference, and it will be considered as what? As noise. Here we have the same frequency and unwanted signal, so it's called what? It's called interference. Now after the channel, I mean the received signal, يعني MR of T, okay, MR of T will be the following: M transmitted of T plus what? Plus I of T. Okay, so interference will be given. Now, M received of T will be MT of T, which is the following: MT of T plus cosine omega CT plus 30 degree. This will be the received signal. Now, what will happen inside the receiving end? In the receiving end, first step, we are going to multiply the incoming signal by what? By cosine omega CT for what? To down convert the frequency, okay? For frequency reduction, to work within what? Within the range of the baseband signal. So, in the receiver side, we have the following signal, which is MB of T equals to MT of T sorry. MB of T equals to MT of T multiplied by cosine omega CT plus cosine omega CT plus 30. Again, it is multiplied by cosine omega CT. Now, to solve such a problem, really, you need two trigonometric identities. First one is cosine squared theta will be 1 over 2, 1 plus 1 over 2, 1 plus cosine 2 theta, and the other trigonometric identity will be cosine A, cosine B, and it will be 1 over 2 cosine A plus B plus cosine A minus B. Okay, so this will be the required trigonometric formulas to solve the problem. Now, after that, you can expand M of T to what? Ms of T cosine omega Ct. So here we have cosine squared, and it will be 1 plus cosine 2 omega Ct. On the other hand, in the second part, again, we have cosine omega Ct plus 30 multiplied by cosine omega Ct. So we have cosine 2 omega Ct plus 30 and cosine 30. The high frequencies, I mean 2 omega Ct, will be cancelled by the filter. So at the end of the day, we have the following signal. I mean MB of T will be Ms of T plus cosine 30 degree. Now, this is inside what? Inside the receiver after frequency down convert. Remaining is what? The remaining will be multiplying by the code sequence C of T. Now, here we have MB of T equals to MS of T by C of T plus cosine 30 degree C of T. Now, MS of T, basically it is what? It is M of T multiplied by C of T multiplied by C of T plus cosine 30 degree multiplied by C of T. Now, we said that we are going to perform the exclusive NOR gate when we have multiplication. And this C of T by C of T is an exclusive NOR gate. So they are the same. So the result will be what? Will be 1. And here the remaining will be M of T plus cosine 30 degree C of T. Again, if we are going to the receiver of the direct sequence separate spectrum, at the end of the receiver, we have a matched filter and a three-shoulder. Matched filter and the three-shoulder means when we looking as what? As integrator, okay, and the three-shoulder. Integration means what? Means finding out the sum of the areas. Now, C of T, if you going back to the C of T, please. C of T, we said that C of T consists of what? 0, 1, 1, 0, 1, 0, 0, 1. Look, please. Within the solution, we said that we are going to transmit the signal using the binary phase shift keying. So we are going to perform the mapping operation. Mapping operation means what? Every 0 is converted to 1. Okay? Every 0 is converted to 1. And every one is converted into what? Into minus 1. Okay? Now, if we are going to, this one again is minus 1. Now, if we are going to perform the summation of areas, look, 1 minus 1, 0. Minus 1 plus 1, 0. Minus 1, I mean this one, in this way, summation of C of T, it will be 1 plus minus 1, plus minus 1, plus 1, plus minus 1, plus 1, plus 1, plus minus 1, and the answer will be 0. So MB of t will be M of t, and M of t is 101. Okay, this example really illustrates how we are going to utilize the direct sequence separated spectrum to transmit and receive a message in binary data. Now, do you have any question, please? Well, now let us take a rest about 10 minutes, and we will go back to continue the lecture. Okay, stop sharing. Yes.